This video could be called AP Chemistry Chapter 6, but we're going to focus on the difference between exothermic versus endothermic reactions and how work plays a part in that. In an exothermic reaction, what you need to keep in mind is that the reactants start out with a higher energy level than the products. So as you notice, the slope on this is negative because the energy decreases. So for our purposes, delta H can be thought of as heat. It's really enthalpy, but because some things are being held constant that we really don't need to deal with, you can think of enthalpy as being a way to measure or a way to think of heat energy, which heat energy we measure in joules. In an endothermic reaction, what you need to know is that the reactants have much lower energy to begin with than the products. So that means, as you notice, the slope of this is uphill. So delta H then is the enthalpy, the heat energy put into it, has to be put into the system, and then delta H is positive. Physical changes can also be endothermic or exothermic. For example, if we start off with a solid and we want to change it to a liquid, we're going to have to add heat energy. Thus, this process would be endothermic. You're putting heat energy into the system. Similarly, if we go from a liquid to a gas, again, you're going to have to add heat energy to it. This process is also endothermic. Working from the other direction, if we start off with a gas and we want to condense it into a liquid, well, that would require the removal of heat energy. So heat energy comes out of this process, so it's exothermic. And lastly, if I want to go from a liquid and freeze it to a solid, again, I have to take heat energy out of the system to get the temperature to lower, and that makes this process exothermic. Is this exothermic or endothermic? Well, in order to decide that, first we have to identify our system. And our system in this case is the piece of metal. So is this piece of metal losing or gaining heat energy? Well, it looks to me like it's losing heat energy. It's putting heat energy out. So the internal energy of the system is going down. This process is exothermic. Take a look at this, endothermic or exothermic. Well, again, we have to define our system, and our system in this case are the globe bracelets. In order to drive the chemical reaction of the globe bracelet, it has to draw heat energy into the system. That makes it endothermic. Well, what do you think? First, let's define our system. In this case, the system is the bomb that went off, clearly releasing a ton of heat energy. So, yeah, exothermic. Exothermic or endothermic? Well, you might have guessed already that the point of view is the ice cube itself. So the ice cube is melting, so it has to draw heat energy into itself to get it to melt, so that is endothermic. Okay, so the ice pack itself. Is the ice pack, that'll be our system. Oh, ignore the dogs, please. So if the system is the ice pack itself, is this process endothermic or exothermic? Well, in order to drive that chemical reaction inside the bag, heat energy has to be drawn into that chemical reaction. So it is endothermic. So here we go. We're just going to say endothermic or exothermic, and of course the system will be identified. So if your hand gets cold when you touch ice, that means heat energy is being drawn out of your hand and into the melting ice cube. So this process is exothermic. Take a look at this one, water boiling. Well, from the point of view of the water, in order to get it to go from a liquid to a gas, you have to add heat energy, so it's endothermic. As water vapor condenses, it's going from a gas to a liquid. The temperature is lowered, and in order to lower the temperature, heat energy has to come out of the system, so it's exothermic. To melt ice cream, you're going from a liquid, no, I said that wrong, from a solid to a liquid. And in order to do that, heat energy has to go into the system, so it's endothermic. Take a minute, pause the video, try to answer this question on your own and see if we agree. Freezing of water is exothermic. It's exothermic because you have to go from a liquid to a solid. You have to lower that temperature, and in order to lower the temperature, you have to release heat. Previous reactions we looked at were, well, they weren't reactions actually, they were physical processes. Now we're going to look at chemical reactions. Of course, you're still going to have to identify both your system, in this case it's the methane, and the surroundings. Well, methane burns. It's a combustion reaction. And in this combustion reaction, heat energy is released. So heat energy is leaving the system and going into the surroundings. It's exothermic. Again, I urge you to take the time to pause the video and try to answer these questions, because if you just go through and you write down what I say, you're not going to learn anything. It's like, writing a list of vocab words for definitions. You can do it without even engaging your brain. Please interact, write them down, try to guess before I tell you the answer. And by all means, if you disagree with me, let me know. Okay, so here we go. We have to define our system. Our system in this case is the water drops. Our surroundings then will be your skin, because what's happening is heat energy has to leave your skin, goes into the water drops, giving them the heat energy they need to evaporate. So this process is endothermic. Okay, we're going to look again at another one. Again, I'm going to give you a minute to pause it. Well, we're talking about a chemical reaction. They react violently. Well, that must mean, yeah, that's your keyword. That must mean that the energy of the potential energy of the reactants was much greater than that of the products. So in this case, the heat energy has to be released to react violently, and this is exothermic. I know this is super twisted, but this is one of my favorite questions. Yeah, I'm giving you time to read it. Time to read it. Okay, well, we're looking at processes that perform work in delta E, so we're probably going to be looking at a specific equation. So this is an endothermic process. So what is the sign of Q going to be? Well, Q will be positive. This system performs work. That means to do work, the internal energy of the system must decrease. So the sign of work is W. But we have a statement that said the work energy is greater than that of the heat. So the value of W will be larger than that of Q, which means your overall sign is negative. Okay, let's try another one. The magnitude of work is greater than the magnitude of heat. Starting off with our equation, let's take a look. It's an endothermic process. Endothermic process means that the sign of Q is positive. It's performing work. That means the internal energy of the system is decreasing, so the sign of W is negative. Well, that means because heat energy is greater, well, the magnitude of the heat energy is greater than that of work, Q overpowers W, and the sign of your energy, delta E, is positive. Okay, work is being done on a gas. The process is exothermic. Well, in this case, exothermic. Well, I know the value of Q now is going to be negative. Work is being done on our system. So if work is being done on the system, the internal energy of the system has to go up. So the sign of W is positive. We also know the magnitude of that number is greater than that of heat. So the work rules the sign of E, positive. This is an interesting concept called gas work. In this particular situation, we have a container holding purple gas. And the purple gas is a certain volume. And we know, thanks to Boyle's law, that pressure and volume have an inversely proportional relationship. So if the volume of this container is decreased, that means the pressure inside the container is increased, we end up with a change in volume of the gas. In this case, work was done on this system. That means the internal energy of the system had to increase. So now I'm going to do some derivations to help you understand this concept from a math point of view. A very long time ago, back in the previous chapter, we defined pressure as being force divided by area, and I'm going to rearrange this equation for force. Having done that separately and independently, in this chapter, we described work as being a force exerted over a change in distance. On the previous slide, we defined the change in distance as the change in height. So I'm going to rearrange work for a change in height. Looking at this equation, we can now look at the force term. Well, force is pressure times area. So I'm going to rearrange, well, actually, I'm going to substitute force for PA. Now, another equation that we've used is the volume equation. Volume is area times height. Well, in this case now, I can substitute V for area times height. And I end up with work is equal to pressure times the change in volume. The only thing left is to look at our sign. In this case, what happened to the volume? Well, if you said decrease, you're the winner. Yes. So our overall equation is work is equal to pressure, the negative pressure, times the change in volume. The sign of work depends a lot on the sign on the volume. For example, in this scenario, I have gas in a chamber with a movable partition. The sign of work, well, you need to ask yourself, what's happening to the volume? In this case, the volume of that container expands. And if it expands, what happened to the value of the height, the change in distance of that container? Well, the change was positive. So the sign on volume is positive, which means the sign on work will be positive. On the flip side of this, if I have the same scenario, but the volume in this case is going to decrease, we call that compression. Well, the change in the distance of the gas, the change in height on that volume decreased. So that means our sign then of work will be negative. Another way you can determine the sign on work is asking yourself, is work being done on the system or by the system? And in this case, because it's expanding, the system is doing the work on the surroundings. So it's by the system. In order to get the system to do work, you have to lower the internal energy of the system. Lowering the internal energy of the system means that the sign of work then is negative. Now, on the flip side of that, if work is being done on the system, that means you are actually increasing the internal energy. I can't talk today. You're increasing the internal energy on the system. And that means the sign on work will be positive.